Hi everybody, welcome to this section 1.3 video. Here we will be introducing differential equations as mathematical models. So in this section, we're going to look at a few real-world situations and see how a differential equation can be created to help produce this mathematical model. So let's go ahead and look at some learning objectives and get started with a few examples. Here, we're going to introduce differential equations as mathematical model, and then we are going to translate real-world applicational models into differential equations. These will be happening at the same time, but they're both important objectives to achieve. So let's go ahead and define what mathematical model is, in case you are unfamiliar with the definition or how it would be applied. So mathematical models as initial value problem. So just remember that initial value problem is just a differential equation with an initial condition. So it is often desirable to describe the behavior of some real life system or phenomenon, whether it's physical, sociological, or even economic. We want to describe these real life situations in mathematical terms. And the best way to describe a real life situation is developing a mathematical model of this situation. That way, we can achieve some certain goals we have of studying this real world situation. So, here are some of the most common ways that you've probably seen before, but let's just restate that say we want to build a mathematical model of a certain ecosystem. We want to see the growth of the populations of animals in that system or species in that system. Radioactive decay, like say we want to be able to see how old fossils are, like saying date fossils by analyzing the decay of a radioactive substance. Okay, so these are just a few examples. We're going to look at a few more situations today. And what we're going to do is see the different type of real world situations and develop these differential equations as a mathematical model. So let's look at the first example, which is going to be population dynamics. So the Malthusian mode by Thomas Malthus in 1798 assumes that the rate at which the population of a country grows is proportional to the total population of the country at that time. Okay, so here we're talking about population and the growth of a population in a country. Okay, so we want to develop a differential equation as a mathematical model. So the goal here is to create a differential equation as a mathematical model, and specifically, we want to create an initial value problem. So we're talking about population. We're talking about the population, the rate at the population grows. So we need to develop a variable for this situation. So since we're talking about population, we're going to let P be the variable. So population. Okay, so that's our variable. We haven't really picked this apart yet, but let's just say P is our variable for this problem. So let's sort of pick apart this statement right here. The rate at which the population of a country grows is proportional to the total population of the country at that time. That's what we want to pick apart. So right away it says the rate. So what does rate mean? Rate means derivative. And we're trying to build a differential equation. So the rate is our derivative of the population of a country. So what we would have here is derivative of population. So dp with respect to time t, that's going to be the rate at which the population changes. Okay, so the rate at which the population of a country grows, and then this next keyword, proportional. So when you see that word within these model questions, what that means, it's really just a constant. Okay, and what we typically designate as the proportional term is K. So we'll say K is proportional. And then we'll just say constant again. Okay, so proportional to the total population of the country at that time. So at that time means to me a initial condition. So I want to create a differential equation. And so the way I would write this is the rate at which the population of a country grows is, so here we'll say dp over dt, the rate is means equal to proportional, that's our k, proportional to the total population of the country at that time. So here I'll say k times our variable p, but with respect to time, so it would be times p of t. Okay, and we're building an initial value problem. I have my initial condition. So one easy way we could do that is saying at, time zero, we have our initial population P naught. Initial condition, initial population. And so we're almost done. We're talking about a country growing. So what we would need to do is make sure that our proportional constant K is always positive for growth. Okay, and that is our mathematical model for the Malthusian mode. So the Malthusian mode is already a well-established differential equation. Okay, we did not just create this right now. It's well established. It's been well used for centuries, but it's just a good practice of breaking it apart and seeing how the statement helps develop the initial value problem and helps create this mathematical model. Okay, so that's our first one. Let's move on to radioactive decay down below. So the rates at which the nuclei of a radioactive substance decay is proportional to the amount of the substance remaining. Okay, so this is similar to what we just did on the previous problem. So won't you go ahead and give it a shot, pause the video, and then we'll come back and work it through. Okay. Okay, welcome back. So hopefully you tried this problem out. Maybe your variable was a little different, but nonetheless, let's go ahead and see how we pick this apart. So what I would pick here to be my variable is it's most common to use, we're talking about rate of decay and substance A. So here I would say A is for my substance decaying. Okay, and same thing, we're talking about proportional. So here I would say, K is my proportional constant. And then we're talking about the rate. So what does that mean? That means derivative. So dA, we're still talking about with respect to time. So dA over dt, the rate. Okay, so let's build up this differential equation. What we would have is dA over dt. Okay, the rate at which the substance decay is proportional to the amount of the substance remaining, and that just means our A of t. Okay, so the amount of substance remaining, that to me signals an initial condition. So the way we would take care of that is we would say, at time zero, we have a certain amount of substance remaining, our initial amount. And last thing to take care of here, we're talking about decaying, so I would need to make sure my constant is negative. Okay, let me make a little note here. This is my initial substance at time zero. And I can make the same note up above. But okay, so here are my two basic mathematical models. We created differential equations, and they are mathematical models for these real world situations. So that's our first attempt at it. And next video, we're going to be looking at a couple more examples, but that's it for this video, and I'll see you in the next one. Okay, take care.